Continue with our electrochemistry. So we were doing voltaic or galvanic cells. Now we're doing electrochemical cells. So remember, these cells, what we're doing right now is we're looking at cells that we have to like connect energy to make them go. So we're trying to make non-spontaneous reactions occur. How do we do that? We add energy. So what about if we have more than one ion? How do we know which one will or won't happen? So it's kind of the same rules we had before. You need to look at the reduction potentials that were given to you. So if you have more than one cation that's present, the one that is easiest to reduce, closest to the top, will be the first one reduced in the cathode, or most positive. Okay. Here's how I don't know, this just works for me. MPR, most positive reduce. Like NPR, like the news station, but MPR, most positive reduce. This is how I remember this. When more than one anion is present, the anion that is easiest to oxidize, closer to the bottom, will be oxidized first, more negative. So more negative oxidized, like LMNOP, like the ABCs. I don't know, just works for my brain. So more positive reduced, more negative oxidized. So all we have to do is look on here. We're going to talk about this water one in just a few minutes, but I want to see this. So if it's more positive, it's more likely to be reduced. More negative oxidized. Now, you're going to see they're probably like both going to be negative or both going to be positive, but whichever one is the most negative will be oxidized. The one that is most positive will be reduced. Okay, so let's look at this. All right, so predict the half reaction occurring at the anode and cathode for the electrolysis of a mixture of molten AlBr3 and MgBr2. Well, we don't have to worry about Br, right? Anion is oxidized, Br is oxidized. We're good. Question is, who's reduced? Okay, so, and just remember this, the anion is always the one that oxidized, the cation is always the one that's reduced, but you also have to remember like bromine has to be oxidized because it can only lose electrons, right? Its highest oxidation state is -1. It is -1 in all these, so it can't do anything else, right? So we're looking here at our cations. So bromine has to be oxidized. Our cations will be the ones that are being reduced. Question is which one's which? So this is just straight from the table. So if we want to figure out which one it is, whichever one is, remember, more positive reduced. So whichever one is more positive, it's going to be the one that's reduced. So if we look at here are our two choices. These are both negative, right? But this one is more positive, right? So because the reduction of aluminum 3+ is a more positive, it is the easiest, and the easiest one will occur. So this is going to be our reduction. And then bromine will be our oxidation. So here's bromines. What's bromine? It's like Br, doesn't really matter. So which one's going to be our anode? Our anode is our oxidation, which is going to be bromine. 2Br-. I gotta look, I don't remember. Where's bromine? All right, got it. So 2Br-, now I just have to remember it long enough, goes to Br2 plus 2 electrons. So that's going to be our oxidation. Our reduction is going to be the most positive one, will be our Al. Al 3+ plus 3 electrons goes to Al solid. Right? So the question is predict the half reaction occurring at the anode and the cathode. This is our anode. And remember, this is going to be our cathode because it's the red cat. Leo, the red cat, reduction at the cathode. And so this is our reduction, our anode and our cathode. Okay, so here all of it is much neater, I'm sure. So again, we decided this has to be our oxidation because anions are oxidized, cations are reduced. Because red cats goes with that, reduction cations, just like reduction at the cathode, they kind of go together. And then we had to pick which one happened here for our reduction, right? One of these two, the least, I'll just say this. I almost said least negative. I'm going to say it in one way to keep it clear in our brains. The more positive one is going to be reduced. Our more positive one is this one. So this will be the reduction reaction. This will be our oxidation reaction. What happens to magnesium? It just sits there and does nothing. Okay, so again, our oxidation one is the one that's more negative. The more negative it is, the easier it is to extract the electrons. The reduction is the more positive. That's the easiest one to accept electrons. All right, let's try another one. Okay. Predict the half reaction occurring in the anode and cathode for the electrolysis of a mixture of MgCl2 and MgBr. Right, okay, well, Mg, that's our cation. That's the one that's getting reduced, right? And you can think of it also like Mg already is Mg2 plus here. It already is Mg2 plus. That's just, it can't lose any more reaction. There's no such thing as Mg3 plus, right? It's as far as it can go. So it is no more, right? So this one will have to be our reduction. Remember, cations get reduced. So this is our reduction. Mg will be our reduction. Reductions at the cathode. So the question is, which one of these two? Is it going to be a bromine or is it going to be chlorine? Remember, anions oxidize. Anions oxidize. Cations reduced. Okay, so which one is it going to be? So we look. Here's chlorine. And here's bromine. More positive reduced, right? More negative oxidized. So we already know, oops, we already know that this one is going to be magnesium, right? Because cations are reduced. So we're not going to talk about reduced. So we're looking for the more negative one. So the more negative one is the one that's going to be oxidized. So who is more negative? Now, both of these are positive, yes, but this is more negative. So this will be our oxidation reaction, right? Okay. All right. So let's look at this one. Oh, look, I have that written right there for you. So you can remember. Anion oxidized, cation reduced. Anion oxidized, cation reduced. All right, so we're going to choose our bromine because it is our more negative one. And here, let me just go back here for a second. So this one's our more negative. And remember, they're oxidations. So these are actually going to go backwards. This is actually going to go backwards, which means these are all both going to switch. But when I'm talking about more negative and more positive, I'm talking about the original reduction potential, okay? Not when we switch it, right? So right now, I'm talking about it looking at this table. This point of view is very important, just like in thermodynamics. I'm not talking about when we switch this. So when I say more negative, I mean looking at the reduction potential. I don't mean go like this. Okay, well then that one's more negative if I flip it. I'm talking about the way it's written on the table. Now, because when we write these as oxidations, so here I am, all I did was I flipped the reactions here. So see, I did this, I flipped these reactions here. And so, and then I changed the way I said it. I'm just gonna make. So I used to say it both ways, but honest to God, it just confused people so much. So I'm just gonna stick to more positive reduced, more negative oxidized, right? Instead of saying least positive, more negative, right? Or vice versa. So the oxidation reaction is going to be the more negative reduction potential, easier to extract electrons, right? Reduction is going to be more positive, easiest to accept electrons. Okay, now here's where we're going to talk about water. Water's kind of messy. Why? Because it's on our reduction chart twice. So this is the reduction equation for water. This is the oxidation for water. Great, awesome, there's two of them. Yeah, great. And again, I'm writing these as reduction potentials because I just want to keep in our brain more positive reduction, more positive reduction, more negative oxidation. And always remember the anions are oxidized, cations are reduced. So I'm just going to go back to the table really fast. I'm going to explain what these are in just a second. I just want to go back to our table so you can see these. I wrote these on the table for us with arrows. I really need to move this. So here's kind of the main water reduction one right here. This is the reduction water. The reduction reaction for water. And this is the one we most often do for the oxidation for water. So again, there's another one up here. We just don't use it as often. This is the one we most often use. Okay, so you just kind of need to remember which ones are which when we're doing this. So let me go back here. And I want to explain what all these other numbers are. Okay. So at standard conditions, the E cell, this means that we need to have a 1 molar solution. Well, that's not the way water really works, right? Because water at any time, right, the concentration is 1 times 10 to the negative 7, 1 times 10 to the negative 7th hydrogen ions, and 1 times 10 to the negative 7th hydroxide ions, right? Because remember KW? It's H plus times OH minus 1 times 10 to the negative 14th. So this one is 1 times 10 to the negative 7. And this one is 1 times 10 to the negative 7. So at room temperature at 25 degrees Celsius, really our concentrations are 1 times 10 to the negative 7th at a neutral pH. 1 molar, not really a reality of a condition. And so at pH 7, this is the actual E cell. At pH 7, this is the actual E cell. And you'll see now, this is the same as this one. When we do this, our oxidation is the same, except for opposite, depending on how you write it. I just flipped it. At 25 degrees Celsius, because the concentration is actually 1 times 10 to the negative 7th. Okay, so these are at, I mean, these are pretty much the same. These ones are going to be the ones on the table, but this is what reality is. I'm just going to only look at this one. That's what the reality of it is. Okay, so what does this mean? So this means that we could possibly oxidize water, or we could possibly reduce water. It just kind of depends, right? And so we're going to look now of, well, which one do we use? So we could have like sodium or water, or chlorine or water oxidized, reduced. So we're going to throw another piece, but the same rules apply. Right? So the same water, the same rules apply here. So for example, if we have Na and I and water, so we have choices. We could have Na, we could have water, oxidize or reduced, or we could have Cl or water. So we just kind of upped our choices. So, but again, the same rules apply. If it's more positive, the half reaction with the more positive E cell is going to be the easiest to accept electrons. So that's going to be reduce. More positive reduce. Same rule applies as we did before. We're just adding in these extra water potentials now. More negative oxidized, the half reaction with the more negative E cell is the easiest to extract electrons. So therefore, when we look at this, you can see iodide is going to be the one that is oxidized. Okay, so here's our choices. So first of all, we have to decide who's going to be reduced. Remember this, cation reduced, anion oxidized. So our cation is our choices for our reduction. So this is going to be reduced. And then remember, we have to remember this is the reduction for water. So our choices are these two. So either this is going to happen or this is going to happen. One of those two are going to happen because this is a reduction. This is a reduction. Again, which reduction is going to happen? We look at these numbers here. With reduction, more positive reduced. Whichever one is more positive, that's the one that's going to be reduced. Our choice is negative 2.71 or 0.41. This one is more positive. This will be the one that's going to be reduced. This one will not be reduced. Next one, oxidation. More negative oxidized. So here's the oxidation for water. Here's our equation for the water oxidation. Anions oxidized. So we have to pick. It's either this one or this one. Whichever one is more negative is going to be oxidized. So our choices are either 0.82 or 0.54. Well, 0.54 is more negative and, right, this is going to be our one that is oxidized. So our choice is not going to be this one. It's going to be this one. It's going to be our oxidation. So iodide is oxidized at the anode, closer to the bottom, easier to oxidize. So what's going to happen at our cathode? This one. This is going to be our cathode. Because remember, red cat. This is going to be our anode. Okay. So if we look at this, again, just to reiterate what we just talked about, we decided either we had to first figure out which reactions are the oxidations, right? So we picked this one and this one. More negative oxidation. So we picked the more negative one. So we said, this is the one that's going to be oxidized. So watch what I'm going to do here with the reaction, just so you can see. I'm just going to flip it. Same thing, but I just flipped it. But I decided this is the one that's going to be oxidized. This is my oxidation, and I flipped it. So my reductions, I said reductions, more positive, reduce. Whichever one is more positive, which is this one, this is going to be my reduction. Right, so that is my reduction reaction. So my overall reaction is just these two summed together. Right, so the same rule that we used at the beginning of class holds. Whoever is more negative oxidized, more positive reduced. You do have to remember the water, which water is the reduction reaction and which water is the oxidation reaction. Right, so remember this, the 0.82 is the oxidation and the 0.41 is the reduction. And well, sometimes we use the 1.23 here too also. So I think it's easiest just to remember the 0.41 because that one's always, or no, sorry, yeah, the 0.41, this one's always a reduction reaction. The oxidation reactions are just the other two. So I always just remember this one. I don't, if anybody has any tricks how to remember this, please let me know. I don't have a trick. I remember that one's the reduction, the others are just oxidation. Okay, so I'm gonna let you think on this one and we're gonna go over this one together. Oops. Look at that. I gave you like part of the answers. Oh, well, you're getting the part of the answers for this one. So for LII, I'm going to give you part of the answers for this one. So I gave you the possible choices for oxidation and I gave you the possible choices for reduction. I just want you to tell me which one happens at the anode and which one happens at the cathode. Okay, so I'm going to give you a couple minutes to try this problem. Just try it and you might get far. It's okay. I'm going to give you like 2 minutes and then we're going to go over this together. So again, I want to know what reaction happens at the anode and what reaction happens at the cathode. So try that and we'll go over it in just a couple minutes. Okay, so again, more negative oxidize, more positive reduced. So our oxidations, we have these to our choice. For oxidations, again, we're choosing one that is more negative. Well, this is more negative, so we're going to choose this one for our oxidation, not this one. For our reduction, more positive reduced. Which one is more positive? Well, this one is more positive. So this is the one we're going to choose for our reduction, right? So when we write this, again, here I have it written as a reduction potential, but it's actually, did not choose this one. We did not choose this one, so we chose this one and this one for oxidation or reduction. So when I write this in the oxidation, see, I just flipped this, flipped it backwards. So now I actually wrote it as an oxidation reaction. So here's my anode, oxidation, wrote it as an oxidation, and here's my cathode, left it as a reduction, right? Sometimes people get confused, like if I say like this is the one that's oxidized, but remember all reactions written on the standard table, we just write everything as a reduction. We had to figure out, okay, what way are we going to write this so it's universal for everyone? So they decided to write everything as a reduction. But again, this positive is written as a reduction. If we flip the sign and flip the arrow, now it's written as an oxidation. To figure out who's oxidized and who's reduced, you want to use the reduction potential straight from the table, right? So straight from the table, that's where we're going to use those. Okay, here's another one to try. I actually put this on here for you. Here's the water oxidation reaction. Here's the water reduction reaction, because sometimes it's kind of hard to figure these two out. Okay, so here's your choices. I want to know what's the anode reaction, what's the cathode reaction, and it's for the electrolysis of NaBrAq, which means it could be Na and water, it could be a Br and water. You get to choose. So try this, and then we'll go over it in just a minute. All right, let's try this one. More positive reduce, more negative oxidized. Sometimes it just gets backwards in our brain. So I just like write that all the time to help. So remember the oxidation reaction, that is more negative, is going to be the easiest to extract electrons. The reduction is going to be the reaction that's more positive, and that's the easiest to accept the electrons. Okay, so we need to decide which ones are our oxidation reactions and which ones are our reduction reactions. So always remember, the anion is always going to be oxidized, cation is always going to be reduced. So our anion, bromine, so this is a potential for our oxide, right? So this is our potential for oxidation reaction. And the other one, I told you, water oxidation reaction, right? And this is other one. Our other one. So it's either this one or this one. So we have to pick this one or this one. More negative oxidized, right? So which one is our more negative here? So either plus 0.123 or plus 1.09. This one is more negative. So this will be our oxidation reaction. So we will not using this reaction. Okay, for our reduction, remember, cations are reduced. So this is an option for our reduction, and this is an option for our reduction. With reduction, whichever one is more positive is going to be the one that is reduced. So our choices are, just put this oxidize on here, negative 0.83 or negative 2.71. So which one is more positive? This one is more positive. So this is going to be our reduction. So now the question is, which one is it the anode and which one is the cathode? Remember, red cat. Reduction happens at the cathode, right? So our cathode reaction is going to look just like this. This is our cathode reaction. Our anode reaction is going to be the opposite of this, right? We need to write it as an oxidation. So if we write this as an oxidation, we just switch our arrow and we just switch our sign, right? That would be our oxidation reaction. We got to switch our arrow. Okay. So let's go over all that again. So we decided that these two are our potential oxidations, MnO, MPr. Whichever one is the most negative is going to be the one that is actually oxidized. So then I wrote it as an oxidation reaction here, and that's going to be at our anode, oxidation at the anode, reduction at the cathode. We had a choice of these two for our reduction. Reduction, whichever one is the most positive is going to be the one that is reduced. This is the more positive one. So this is our reduction reaction. We just write it as is, reduction at the cathode. Here is our reaction. Now, if we wanted to know the E cell for this, which I didn't ask you on here, but like if we wanted to do the E cell, you do it the exact same way. We just add this plus this. And again, look, it's negative. It's going to be, it's a non-spontaneous reaction. But remember, this is electrolysis. And in electrolysis, we're going to add energy to make it go the other way. So even though this is obviously going to be a non-spontaneous reaction, again, how do we know it's a non-spontaneous reaction? It has a negative E cell. But again, this is electrolysis. So we're going to add whatever voltage it is when we add this, 2-ish something. We're going to add 2+ volts to force it to go the other way. Okay. Now, the stoichiometry of electrolysis is actually pretty fun and there's not a lot of brains involved in this one, so you can give your little brain break for this part. So when we're doing the stoichiometry of electrolysis, we can figure out it's related to the number of electrons. So remember today when we did our quiz and we were balancing our redox reactions, the number of electrons, again, that's the number of electrons that you cancel out in the redox reaction. So the number of moles of electrons depends on, again, a couple different things. Now, it's what we get when we balance out our reactions, but there's a couple pieces here. Just so you know, 1 amp is a coulomb of charge per second. So 1 amp equals 1 C per S. You're going to see it's going to be a conversion we're going to use. And a mole of electrons is 96,485 coulombs of charge. 1 mole equals 96,485 Cs. So we're just going to use these two as unit conversions. You don't need to memorize either of these unit conversions. I will give you all of them or both of them. So you can see here, we're just doing a half reaction. The number of moles is 3. So we have 3 moles of electrons. This is 5.5 amps. 5.5 amps, again, that is saying the same as 5.5 coulombs per second. And then we have our other conversion, which is using Faraday's constant. So remember, this is the same thing as 5.5 amps. Right, this is our conversion. Here's the conversion I just showed you with Faraday's constant right here. This again is another constant or another conversion we're going to use. And the rest of them, pretty easy. This is our 3 moles of electron for every 1 mole of AU, and we want the mass of AU. So now it's just really a stoichiometry problem. So you want to calculate the mass of AU that can be plated in 25 minutes using 5.5 amps for this half reaction. Okay, so 2 different places we can start. So we can either start with 25 minutes or 5.5 amps. So some of you had me in like 209, and I taught this in 209. Whenever you're doing stoichiometry and you have a choice to start with something that has 1 unit or 2 units, always use 1 unit. Now, sometimes you don't have a choice, but sometimes you do. 25 minutes, that's 1 unit. Amps is 2 units. It's coulombs and seconds. So if you ever have a choice, this goes for, you use this on your final, 1 unit or 2 unit, start with 1 unit. So if we start with 25 minutes, yeah, can't really do anything with the minutes, right? But there's a seconds here. So if I can just change my minutes to seconds, I bet I could do something with this conversion. So right, in 1 minute, there's 60 seconds. Now I can use this. So 5.5 amps is the same thing as 5.5 coulombs per 1 second. Units. And then I've got Faraday's constant here that I can use. In 1 mole of electrons, there's 96,485 coulombs, units. Moles of electrons. And again, where did I get this 3? I got it from my half reaction right here. There are 3 moles of electrons in 1 mole of AU. And again, whoa, where did I get the 1 mole here? It's use stoichiometry. There's 3 electrons and there's 1 AU. That's where I got it. And then I use molar mass, periodic table. In 1 mole of AU, we get 196.97 grams. So this isn't so bad. And then in the end, we get grams. And so that's so bad with the stoichiometry. There's a couple new pieces, right? This, remember, is the same thing as an amp. This is 5.5 amps. And this is just Faraday's constant, Faraday's conversion. And again, this is the number, this right here is those moles of electrons from your half reaction that you used. All right, so let me see here. Oh yeah, nice, got that here for you. There we are. And you end up with 5.6 grams of AU. And then all of our conversions cancel out super nicely. And there we are. Okay, so remember these conversions. And 1 amp is coulombs per second. So now I want to know the amps. Now I want the amps. So this time I want the amps. Remember, amps is coulombs per second. 1 amp is coulombs per second. Required to plate 2.5 grams of gold in 1 hour. All right, so I'm going to give you a minute just to brush up on your stoichiometry, and then we'll go through this together in just a minute. Okay, so try this one, and we'll go over Taylor in just a couple minutes. All right, let's try this one. So in this case, you can kind of start with either of these. You'll kind of see that it only works. We try it one way, because if we want, in the end, remember, we want amps. Remember, amps is coulombs per second. So they're telling us it's 3,600 seconds. And so we somehow need to get grams to coulombs, which we can do that. To go back, we can go from grams to moles, and then we can use Faraday's to get there. So we start with 2.5 grams, use our molar mass in 1 mole. Then we can use the electrons in 1 mole of AU. There's 3 moles of electrons. Again, this is where this conversion came from. Faraday's is the big one. In 1 mole of electrons, there's 96,485 coulombs. And again, amps is coulombs per second. So if we get our coulombs here, we just need our seconds on the bottom, because all these cancel off. And 3,600 seconds. And there we are, we've got coulombs over seconds, and that is amps. I'm not sure what this adds up to. Some people don't like just doing this with this blank. I don't know, put a smiley face there. You could do it in 2 steps. I just always do my stoichiometry in 1 step, but it's really whichever one you prefer. I think my solution has it in 2 steps. So again, it's just straight stoichiometry. This is a new conversion for us, and using this is a new conversion for us. The rest of it is what we've done before. So here it is in 2 steps. So here, cross off my units. I got my coulombs, and then I got coulombs per second is amps. Oh, and look it up. It's 1.0 amps. All right, any questions on this one? Questions on this? Hopefully just a little bit new stuff, not too new, just a little bit of new. Okay, now we're going to talk briefly about corrosion, because it's kind of a very great thing for electrochemistry and completely applicable to our lives. So what is corrosion? So corrosion is just the spontaneous oxidation of a metal by chemicals in the environment, mostly oxygen. So many of the materials that we have are active metals, and so corrosion is a really big problem, because why do we use metals? Because their strength and malleability, right? All the properties of metals. But some metals, when corrosion occurs, actually makes them stronger, and some disintegrate. It depends on the metals. So we're actually going to look at a couple different metals. Okay, so oxygen is going to be doing the oxidations, right? So oxygen is very easy to reduce in moist conduction. So our oxygen is going to be our oxidizing agent, right? So here's oxygen, give it a little bit of water, and it undergoes reduction spontaneously. You add a little acid to it, it's even more spontaneous. So you can see plus 0.4, 1.23, that this is definitely big happy reaction here. Now, the reduction of most metals lies below oxygen on the reduction table. So that means that oxygen is going to oxidize those metals. So the metals lie below oxygen. So oxygen is going to go in the forward reaction. The metals will go in reverse reaction, and they will be reduced or oxidized. Oxygen will be reduced, right? So here's our oxygen. It's going to go in our forward direction. I think I only have this one. So I'm going to put, this one would be way higher. So here the 1.2.3 one is up here, but here's our oxygen, and you can see most of our metals are below it. So remember, when we're looking at this reduction table, if the reaction above is paired with one going in the reverse direction below, it is a spontaneous reaction. So this will be reduced, and all of these will be oxidized if paired with this reaction, right? So when we look at this, let's just look at our aluminum, which do I have aluminum on here? No, I don't have aluminum here. Okay, so aluminum is still below oxygen, by the way. But when it oxidizes, it actually oxidizes to aluminum oxide. And aluminum oxide is it's like it seals the aluminum. So you probably all have seen it. It's like a little bit darker than aluminum. It's kind of like a black gray, and it actually seals it. So remember in lab when we were adding that aluminum wire, and I told you that, you know, we know it's not working that well, and we tried to sand it to see if that would work, because what we thought was maybe the aluminum had oxidized in the environment to aluminum oxide, and aluminum oxide, it's like it makes like a coating around the aluminum, so the aluminum is impermeable to the oxygen, and it's this hard coating. And so if we sand it off, maybe it will work better. It didn't, but that was our hope. Now iron is different. When iron oxidizes, it becomes structurally unstable, and we've all seen what happens when iron oxidizes. That's rust. It flakes away, flakes away, flakes away, flakes away until no more oxygen. So some metals just oxidize in a way that makes them stronger, some weaker. If you look at the Statue of Liberty, that's an example of stronger. And I don't know if we'll have time to talk about that today, but maybe. Okay, so what happens in rusting? Okay, so I think I wrote these numbers down so I can remember. So you can see how spontaneous these reactions are. So, okay, so we have these anodic regions that are anodes where oxidation happens, and these cathode regions where cathode reduction happens. So in the anodic regions, the Fe is oxidized to Fe2+. So first of all, how does this happen? The iron has to get exposed to the air somehow. That's the only way. So if we coat the iron with something that doesn't expose it to air, then it won't rust. So that's why, like cars and such, like we coat them with the coating so they don't rust. That's why, like, if you have like the railings, you paint the railings, right? The iron railings, so they don't rust. But let's say they get scratched, then that's where our oxidation starts. So what happens with our oxidation? We have iron going to Fe2+. In lab, we've seen this Fe2+. It's a really pretty, like, I think I have like a color. It's like this really pretty, like, sea green color. It's super pretty. It's more of like a blue green. I can put these on top of each other. That's kind of, it's like a blue-green color. It's very pretty. Okay, this potential is, E is negative 0.45. Really hurt my hand. Negative 0.45. Okay, so that's the first thing that happens. And then the electrons travel through the metal. They travel through the metal. And to our cathodic region where oxygen is reduced. Now, if it's an acidic reaction, this is like super fast and super amazing. So if it's an acidic reaction, this is my acidic reaction. It's just 1.23 volts. This one right here. So if we put this together right here, you can see this is, what is this when I added this up? Flip this one over. You can see it's a pretty spontaneous reaction, right? So in an acidic solution, this happens even faster than in a neutral solution. So what happens after this? Then you have, this is like a water droplet, by the way. See, this is a water droplet. This whole thing is happening in a water droplet because it has to have water. It doesn't happen without moisture. It has to happen with water. So then what happens in the water droplet is we have another oxidation where this pretty little Fe blue turns into this. And that is rust. So it further oxidizes to rust. Okay, so in order for rust to happen, you got to have water. You got to have water for rust to happen. And if we have an acid involved, it goes even faster and it's more spontaneous. Well, where does this acid come from in the environment? Well, water, while it rains, runs into CO2, and guess what it makes? Carbonic acid. That's where the source of the H plus comes from. So that's where our H plus is coming from. It's coming from the carbonic acid when water combines with CO2, which is already in the atmosphere. Now, if you have acid rain, which uses even stronger acids, more H pluses, this will happen even faster. Okay, so let's summarize our rusting. So what is rust? It's just hydrated iron 3 oxide. That's what rust is. You gotta have water. So in order for something to rust, you have to have water. And if you add an electrolyte like salt, this even happens faster. Now, has anybody, I don't know if anybody's ever lived in like the Midwest or the Northeast where it snows. People don't really have nice cars there. Or they have winter cars and they have summer cars. And it doesn't necessarily mean like nice and not nice, but if you live in the mountains where it snows a lot, they put salt on the roads to melt the ice, right? And so you're always getting salt in your underside of your car. And so cars in the Midwest and the Northeast rust so much faster than cars here. Why? Because it's wet and there's salt. So you've got your water and you have your extra electrolyte, your NaCl, flowing through it. Some people who live close to the ocean, we have the same issue. If you live close to the ocean, like here in Southern Orange County or Orange County in general, well, half of California has this problem, right? Because the salt from the air continually, right, with the marine layer comes in, gets on our car, and then rusts our car or rusts other things. So in Orange County, we have this problem of rusting happens a lot faster than, let's say, if you were in Riverside, because we have that salt, which is adding an electrolyte to our rusting. So our cars rust not as fast as in the Midwest and in the Northeast, but they can rust. but that's how we put the coating on the cars. But if the car gets a scratch on it, then it rusts even faster. Okay. Now, how do we prevent corrosion? So one way to prevent corrosion or to slow it down is to coat the metal surface, right? So sometimes we use paint for this, or again, aluminum, when it oxidizes, it's actually stronger. Did you know that nails, we figured out with nails. So if you ever look at a nail, they're like shiny, but really a nail is iron. But then nails rust. Ever seen like a rusty nail? Because if nails were only iron, they would rust. And so what they do is they coat nails with zinc. Zinc is below iron on the chart. So here's our oxygen, here's our iron, and here's our zinc. And so remember, one of these two are going to be oxidized. Well, this one is more negative, so it's more negative oxidized. It's below it. So this is going to be oxidized first, and which saves our iron. So our iron isn't oxidized. So zinc will oxidize, zinc will oxidize, zinc will oxidize. And eventually if the zinc disappears, then the iron will start to oxidize. So if you ever see like nails, that's why we have a galvanized nail. It's just iron coated with zinc. And again, either iron or zinc is going to oxidize. Zinc is below iron. It's more negative. So it oxidizes first. So when you see a rusty nail, all the zinc has been oxidized away, exposing the iron. And that's where we get our rusty nails. So that's why old nails or nails that are exposed to a lot of water or salt, they're going to oxidize much faster, and then they become rusty nails much easier. Another thing we could do is add what's called a sacrificial electrode. So a sacrificial electrode, this is how they like save like pipes and underground water tanks and things of that sort. This electrode is going to be, usually it's like magnesium or aluminum or something of that sort, something below iron on the table. Because again, one of them is going to be oxidized. But so if you have iron, we'll just put like magnesium down here or aluminum. So these will be oxidized first, saving our iron pipe. So they're going to oxidize before iron, which prevents iron from corroding. Because remember, when aluminum oxidizes, it makes aluminum oxide, which is actually stronger. Same thing with magnesium. Magnesium oxidizes and turns to magnesium oxide, which is this black coating too. And so they will both be oxidized before iron. And so you have to check on this and like replace the sacrificial electrode every once in a while. But that's how you can still have iron pipes and things of that sort, which we're kind of replacing those all with plastic now, but that's how you could do it. You could use these sacrificial electrodes. So they get oxidized before iron does. Okay, so that is the end of our electrochemistry. Okay, so